Question number 1. A company is building a serverless application that runs on an AWS Lambda function that is attached to a VPC. The company needs to integrate the application with a new service from an external provider. The external provider supports only requests that come from public IPv4 addresses that are in an allow list. The company must provide a single public IP address to the external provider before the application can start using the new service. Which solution will give the application the ability to access the new service? Question number 2. Example Corporation has an on-premises data center and a VPC named VPC-A in the Example Corporation AWS account. The on-premises network connects to VPC-A through an AWS site-to-site VPN. The on-premises servers can properly access VPC-A. Example Corporation just acquired any company which has a VPC named VPC-B. There is no IP address overlap among these networks. Example Corporation has paired VPC-A and VPC-B. Example Corporation wants to connect from its on-premises servers to VPC-B. Example Corporation has properly set up the network ACN and security groups. Which solution will meet this requirement with the least operational effort? Question number 3. A company has migrated a legacy application to the AWS cloud. The application runs on 3 Amazon EC2 instances that are spread across 3 availability zones. One EC2 instance is in each availability zone. The EC2 instances are running in 3 private subnets of the VPC and are set up as target for an application load balancer that is associated with 3 public subnets. The application needs to communicate with on-premises systems. Only traffic from IP addresses, company IP addresses range are allowed to access the on-premises systems. The company security team is bringing only one IP address from its internal IP address range to the cloud. The company has added this IP address to the allow list for the company firewall. The company also has created an elastic IP address for this IP address. A solution architect needs to create a solution that gives the application the ability to communicate with the on-premises systems. The solution also must be able to mitigate failures automatically. Which solution will meet this requirement? Question number 4. A company needs to migrate an on-premises SFTP site to AWS. The SFTP site currently runs on a Linux VM. Uploaded files are made available to downstream application through an NFS share. As part of migration to AWS, a solution architect must implement high availability. The solution must provide external vendors with a set of static public IP addresses that the vendor can allow. The company has set up an AWS Direct Connect connection between its on-premises data center and its VPC. Which solution will meet these requirements with the least operational overhead? Hello everyone. My name is Rafi Saeed and I'm thrilled to have you with us for another 591 Lab video. Today our spotlight is on AWS Solution Architect Professional Exam, a certification that stands out for its advanced level and industry demand. Whether you're gearing up for the Solution Architect Professional C02 exam or you're Cloud Architect or System Admin, this video is tailored to provide you with the insights you need. But before we dive into the content, we have a humble request. Please subscribe to our channel, like the video and hit the bell icon. Your support goes a long way in enabling us to create more valuable content like this, helping you excel in your cloud journey. So our today's session is divided into 2 sections. First, we'll explore advanced features of Virtual Private Cloud, VPC, covering aspects like VPN, NAT and Transit Gateway. In the second section, we'll solve few exam questions to ensure a comparative understanding. But before we jump in, let me give you a bit more insight into what 591 Lab is all about. 591 Lab is a top IT training and certification exam brand in China, Hong Kong, Taiwan, and Singapore. Our mission at 591 Lab is to provide our clients with exceptional exam preparation experience for certification in AWS, Cisco, Huawei, Aruba, Juniper, Palo Alto, and Fortinet exam tracks. In today's agenda, first we'll cover VPC key components, management and best practices. After that, we'll zoom in VPN, NAT and transit gateway. We'll follow it up with hands-on labs where we'll log into the console for practical experience. Moving on the second section, we'll tackle few exam questions to put your knowledge to the best and ensure a clear understanding of AWS Solution Architect professional exam topics. So buckle up for an insightful and hands-on session. Let's get started. So VPC is a logical isolated section of AWS where you can launch AWS resources in a virtual network that you define. Think of it as your own private space in the cloud, providing flexibility and control over your network infrastructure. Solution Architect Professional is an advanced level certification, so I am assuming you're already familiar with VPC basics. So let's quickly revisit the fundamentals for a brief recap. Key components of VPCs are subnets, which divides the VPC IP address ranges, enabling segmentation of resources. Subnets are associated with specific availability zones and can be public or private. Route table define rules for routing traffic between subnets that are used to determine where network traffic is directed. Each subnet in a VPC must be associated with a route table which controls the traffic leaving the subnet. Security groups act as a firewall controlling inbound and outbound traffic to AWS resources. You can specify rules that allow traffic to or from instances based on IP addresses, ports, and protocols. Network ACLs provides an additional layer of security at the subnet level for controlling traffic in and out of one or more subnets. Before deploying a VPC, there are several best practices for VPC management. Plan your IP address range carefully to avoid future conflicts. Use multiple subnets for best resources organization and security. Spread resources across multiple availability zones for high availability. Use security groups of control inbound and outbound traffic to instances. Implement network ACLs for additional control at the subnet level. And place sensitive resources in private subnet and use net gateway for outbound access. These are the fundamental aspects of VPC that should be considered before deploying a new VPC or implementing any changes in an existing one. Now let's proceed to the next slide. AWS Site-to-Site VPN is a secure and scalable solution for connecting on-premises data centers to AWS VPCs over the internet. The key components of AWS VPN are Customer Gateway, which represents the on-premises VPN devices, Virtual Private Gateway, the VPN endpoint on the AWS site, and VPN connection establish the secure link between Customer Gateway and Virtual Private Gateway. The key benefits are secure communication, encrypts data in transit, ensuring secure communication between on-premises and AWS, scales to accommodate growing network requirements and additional VPN connection, high availability support multiple tunnels for automatic failover, ensuring continuous availability. With the help of VPN, you can connect on-premises data centers to AWS for hybrid cloud architectures, facilities secure migration of workloads from on-premises to AWS, and also you can connect your remote offices securely to AWS resources. AWS Site-to-Site VPN enables secure communication between your on-premises data center and the AWS cloud. It establishes a virtual private network connection over the internet, extending your on-premises network to AWS for secure and scalable connectivity. Now, let's proceed to the next slide. Net Gateway is a managed AWS service that enables instances in a private subnet to initiate outbound traffic to the internet while remaining secure. Consider implementing Net Gateway when your private instances need outbound internet access for activities such as update or license activation. This ensures security by avoiding the exposure of private IPs, offering the advantage of consistent static public IP addresses and allowing only outbound traffic while automatically blocking all direct inbound requests over the internet. Consider deploying Transit Gateway in scenarios where your AWS environment include multiple VPCs within a region or spans across different AWS regions, necessitating secure communication or connection to on-premises data centers. Transit Gateway acts as a central hub for managing traffic flow, offering a more efficient and direct communication route compared to traditional point-to-point peering connections. It effectively streamlines communications and connectivity across diverse network segments. NAT Gateway is used for providing private instance in a VPC with outbound internet access, maintaining security by not exposing private IP addresses. Transit Gateway serves as a centralized hub, streamlining communication across multiple VPCs within a region or across different AWS regions, as well as providing secure connectivity to on-premises data centers in complex network architectures. You can utilize either NAT Gateway or Transit Gateway based on your specific requirements and network architecture. Let's dive into the console to explore how we can leverage VPN, network address translation, or NAT gateways and transit gateways to establish secure connectivity. Alright, so we are logged into the console. First, we will explore how to create and use a NAT gateway to enable internet access for instances in a private subnet, while keeping them secure from inbound traffic. This is useful for scenarios where you need to run applications or services that require internet connectivity, such as software update, backups, or API calls, but you don't want to expose your instance to the public internet. In this lab, we will create a NAT gateway in a public subnet and configure a route table and a security group to allow outbound traffic from private subnet through the NAT gateway. To create a NAT gateway, you need to have a VPC with at least one public subnet and one private subnet and an internet gateway attached to the VPC. You also need to have an elastic IP address that is not associated with any instance or network interface. If you don't have these resources, you can create them using the VPC wizard or the AWS CLI. For this lab, we will use an existing VPC with two public subnets and two private subnets and an internet gateway. We will also allocate a new elastic IP address for NAT gateway. So in the navigation pane, choose NAT gateway, create NAT gateway, specify a name, specify the subnet in which to create the NAT gateway and select the allocation ID. So we are going to create a NAT gateway in our public subnet. So I'm going to use my 591 lab VPC 1, this one, but let's choose public subnet from this list. Alright, so this is our 591 lab VPC 1 public subnet 1. So we'll select it and we will leave the connectivity type as default. Now allocate an elastic IP address. So this elastic IP address will be associated with our NAT gateway. And let's create a NAT gateway. So while NAT gateway is in pending state, I have already provisioned an EC2 instance which is on public subnet, and I have already also provisioned a Linux instance which is on private subnet. So let me show you within my EC2 dashboard. So as you can see, there are two instances. The Windows instance is currently on public subnet. So this Windows based instance is currently on public subnet, and the Linux one is on private subnet. Alright, so logged into the Windows based EC2 instance first. Okay, so we are logged into our EC2 instance and we need to connect our private Linux based instance within our public machine. So For this, we have to open PuTTY. Also, we need private instance IP address, which we can obtain from here. So let's copy this IP address and jump back to the Windows-based machine. Let's paste the IP address there. Also, we have to browse the key for access this private instance and click open. Username is EC2-user. Alright, so we are successfully logged into our private instance. Let's try to ping any public website from our private instance. As you can see, this instance is basically not connected with the internet, so we are not able to ping anything. So what we are going to do here, we will add our NAT gateway, and which should be created. So let's jump back to the VPC console and verify the NAT gateway, and then we will add the route to make the connectivity, public connectivity for our private instances. Alright, so our NAT gateway is currently in available state. So to enable the instance in the private subnet to access the internet through the NAT gateway, we need to update the route table for the private subnet. So let's navigate to the route tables. So this is VPC1, private route table 1. So let's click on it and go to routes, click edit routes. So currently there is only one route which is local, which means all the instances or services within this prefix or CIDR block will able to communicate over the local network. So we need to add another route so the instance will start communicating with the internet as well. So let's click add route. We will choose 0.0, which represent all IPv4 in the globe. So the target should be our NAT gateway. As soon as you select NAT gateway, it will start populating here. So let's select your NAT gateway and click Save Changes. Alright, so let's jump back to the instance and verify the internet connectivity. Alright, so we are now able to see the output showing the response time and the number of packets sent and received. So if the ping is successful, it means that the instance can reach the internet through the NAT gateway. Alright, so let's jump back to the console. Alright, so now we'll explore the Transit Gateway, a service that simplifies the connectivity between multiple VPCs and on-premises networks. It's like a centralized hub for your network architecture, making it easier to manage and scale. But before we begin, ensure you have multiple VPCs created. So we have two VPCs, 591 Lab VPC1 and VPC2, which we are going to use with the Transit Gateway. So let's click on Transit Gateway, scroll down the left navigation pane, and from here you can find Transit Gateway. So click on Transit Gateway. To create a new Transit Gateway, click Transit Gateway. Specify a name. Description is optional. You can leave it or provide any description as per your need. And this is also a default configuration, but if you want to specify any ASN name, so you can specify from here, or you can leave it as default. So We don't need to make any changes as of now, so let's create a transit gateway. Alright, so our transit gateway has been successfully created and in available state. So now let's click on transit gateway attachment. Create transit gateway attachment. Specify a name. From here we need to select our transit gateway. So this is the one we have just created, and there are several other options as well. You can attach VPNs, pairing connections, or connect connections. So in this particular case we are going to attach VPC, so we will leave it as default. So VPC is just fine. Alright, so from here we need to select the VPC which we want to attach with the transit gateway. So first we will select the VPC one. Let's select it. All the subnets are selected, so which is just fine. Let's create transit gateway attachment. Now make another attachment for the VPC2. So let's create again on transit gateway attachment. Specify a name. Transit gateway, select the transit gateway ID. Attachment should be VPC, and now we are going to select VPC2 and let's create the transit gateway attachment. Alright, so both VPCs attachments successfully created, and now we need to configure route tables. So click on route tables. So we are working with two different VPCs, Final Lab VPC1 and VPC2. And I have also provisioned EC2 instance on VPC2 as well. Previously, when we are testing NAT gateway, so we just launched two instances on VPC1. But we have now one more instance on VPC2, as you can see there. So this is our Linux-based instance on Final Lab VPC2. Alright, so we need to create a route associations first, then we will test the connectivity. So this is my VPC1 public route table. Let's click on routes, click edit and add route. So we need to specify VPC2 CIDR block here. So the CDR block is 10.20.0.0/16. And in the target we need to select transit gateway. So let's click on transit gateway. The attachment will automatically pop up. So this is the VPC1 attachment. So let's select this attachment and click save. Alright, so now we need to do the same thing with the VPC2 private route table 1. So let's find VPC2 private route table. So this is VPC2 private subnet 1 private route table. So this we need to select this route table, click routes and edit route. And now we need to specify the VPC1 CIDR block, which is 10.10.0.0/16. And in the target we need to select transit gateway, and the appropriate attachment will automatically pop up. So we need to select this one and click save changes. Alright, so now it's time to put it on the test. So we have to log into the Windows based instance which we have created earlier. Okay, so this is our EC2 instance which is running on VPC1, 591 Lab VPC1 on public subnet. So what we are trying to do here, we are going to ping our VPC2 private machine from VPC1 public machine. So let's open command prompt. And for ping we need IP address as well. So let's grab the IP from here. Just copy this IP address and we can ping from here. Alright, so as you can see, we have successfully established a connection between two VPCs with the help of Transit Gateway. So this is basically a Windows machine which currently does exist on VPC 1, which you can verify from EC2 dashboard. So this is our EC2 machine on VPC 1. Alright, so this is VPC 1 and the CID block of this VPC is 10.10. On the other end, we have our private instance which is on VPC 2. So this is our private instance which is on VPC 2, as you can see there, and the CID block of this VPC is 10.20.0.0. So both VPCs are able to communicate with each other over the private network with the help of Transit Gateway. Let's try to take the session of this instance by the help of PuTTY. So we need to paste the IP address here. Also for the key, we have to browse the authentication key here. So we are going to use the same key because I have provisioned both machines with the same key. So let's open. And we are successfully logged into our private instance, which is running on our VPC 2. So this is how Transit Gateway works. Suppose you have three VPCs, VPC A, B and C, which are hosting different applications or services. To simplify network management and streamline communication between these VPCs, you can use Transit Gateway, which provides a scalable and efficient network architecture, allowing seamlessly communication between your 3 or more VPCs. So you can make connection between different regions as well, or with on-premises network as well. So let's jump back to the console and where we are going to explore VPN connectivity between two regions. Alright, so now we'll setting up an AWS site-to-site VPN connecting our on-premises environment, which is located in Oregon region. Because for this lab demonstration, I will going to use Oregon VPC, which is located here. So as you can see, I just name it on-premises VPC. So we are going to consider this network as an on-premises network because we don't have any firewall now. So we are going to use this network. So the main purpose of this lab is to establish a connectivity between two networks over the VPN. Alright, so in the first step, we should have EC2 instance on our on-premises Oregon network. So I have already provisioned an EC2 instance. So as you can see, so this is my on-premises server where we will configure VPN configuration with OpenSWN. So this is already provisioned, so you have to make sure you have provisioned any Linux based instance or Windows based instance, depends on your requirement, on the network where you want to make connectivity. So this is basically running on premises VPC, which is currently exist within Oregon region. So let's jump back to our management account, which is in California region. So first thing first, we need to create a customer gateway. So let's select customer gateway from left navigation pane. Create customer gateway. Specify a name. We can leave BGP ASN as default, or if you want to specify any number, So you can specify from here. And here we need to specify the server IP address, which we can obtain from EC2 dashboard. So this is our OpenSWAN server. Let's click on it and grab the IP, the public IP. So let's copy this IP and jump back to the VPC and paste it here. Alright, so that's it. Just create customer gateway. And now we need to create a AWS site, which is virtual private gateway. So let's select virtual private gateway. This is AWS site, and create virtual private gateway. Specify a name. And just create VGW. So we need to attach this virtual private gateway with the VPC. So in this lab, we are going to use VPC1, as you can see. So we have two 591 lab VPCs. So we are going to use VPC1 for this lab. So let's jump back to the virtual private gateway and attach that gateway with the VPC1. Just select the gateway, click action, and attach to VPC. From here you can select the VPC which you want to connect to. So we are going to use VPC1. So let's select this VPC and attach to VPC. It is now currently in attaching state. So let's wait for a while. Alright, so the VGW is attached now. And in the third step, we need to create a VPN connection. So let's click on site-to-site VPN connections. Create VPN connection. You can specify any name of your choice. So target gateway type should be virtual private gateway. So this is automatically selected. So let's leave it. And from here we need to select our virtual private gateway, which we previously created. So just select this VGW. And we have already created a customer gateway, so we will choose existing. From here you can select your customer gateway. And for routing, we are going to use static because we don't have created any BGP route. So let's select static. So local IP is a CIDR block on customer end or on-premises network. So our on-premises network CIDR block is 172.31.0.0. So we need to specify this CIDR block here. And on the remote network side, we have to specify our California region CIDR block, which is 10.10.0.0/16. Tunnel 1 and Tunnel 2, those are basically optional configurations, so we are not going to make any changes and just create our VPN connection. So the VPN connection is currently in pending state, so let's wait for a while. Once it's available, then we will start configuration of our OpenSWAN server. Alright, so the VPN connection is available now. Let's refresh it. Select the VPN connection and download the configuration file. So we will select OpenSWAN from this list. But if you have any kind of firewall on your on-premises network, or you want to use VPN connection with any different kind of platform or firewall, so you can select the desired configuration from here. So let's scroll down and select OpenSWAN and download the configuration file. So this is our configuration file. So this is the configuration file which we are going to use during the configuration of OpenSWAN server. So let's minimize it for now. Now we need to configure our OpenSWAN server. So we need to access our EC2 machine. So let's jump on the EC2 dashboard. So this is our OpenSWAN EC2 machine. Let's click connect. From here, we need to select the command which we are going to use to make the connectivity. We need to select the directory where our key pair is stored, which is currently in downloads folder. And let's paste the command. Click enter. Alright, so we are successfully logged into the console. Alright, so let's clear the screen. And we need to change our privilege to the root user. So type sudo su. Alright, so first we need to install OpenSWAN server. Alright, so it's installed successfully. Now we need to follow the instruction which we have downloaded from the dashboard. So first we need to open etc sysctl.config file, and we need to paste all this information over there. Alright, so first we need to edit this directory. So this is a directory which we want to modify, and let's copy the configuration from here and then just paste it. Save the modification and exit. For verification, we can open the file again. So yeah, all the configuration is stored in this file. So let's close it. Now we need to run this command. Click enter. Alright, so it's successfully executed. So let's jump back to the configuration file. So this step is basically completed. Now jump back to the step 3. From here we need to modify this IPsec configuration file. So let's copy this path, type nano and click enter. So here we need to paste the configurations for tunnel 1. So this is our tunnel 1 configuration, but before paste this configuration over to the SWAN server, we need to change some configuration. So within the left subnet, which represent the customer end, we need to specify a CIDR block 172.31.0.0. This is our customer site or Oregon VPC CIDR block, and on the Amazon side we have 10.0.0 10.0.0/16. So this represent Amazon site connection or CIDR block. Also, we need to remove this auth ESP option from here. So let's remove it and just copy and paste this to this file. So let's paste it here, save it and exit. Alright, so the next step is to modify the secret file. So we need to modify this secret file and paste this value. Right, so let's jump back and type nano. Copy the secret from here and just paste it. Save this file as well. And now we need to run systemctl start IPsec. This will start the IPsec tunnel. We can check the status as well. Alright, so the service is successfully active and running. Now we can verify within the VPC dashboard. Alright, so as you can see, our tunnel 1 is successfully up and running. You can see the status within the VPN connection. So we have only worked on tunnel 1. This is why it's showing up and running. So now we need to test the connectivity by logging into the EC2 machine. So let's log in EC2 public server first. Alright, so we are successfully logged into the Windows based server, which currently does exist in the VPC1 within a California region. So we need the private IP address or our OpenSWAN server. So let's grab it quickly from the console. So this is our OpenSWAN server. We can copy this private IP address and jump back to the EC2. Alright, so ping is not established as of now. We need to do some configurations, updates the route. So let's jump back to the VPC dashboard. Connection is not established because we have to enable route propagation within our route table. So this is the VPC we are using. Alright, so let's click on route tables, and the Windows machine is basically on our public subnet on the management site, or you can say the Amazon site, where we have created the VPN and all the customer gateways and VGWs. So let's select this public route table. So our Windows machine is basically running on this public subnet, or routing is performed basically with the help of this route table. So let's go to the route propagation and click edit route propagation. Just enable it and save it. So now we can verify by logging back into the EC2 machine to see if the communication is established or not. Alright, so we are successfully able to ping our OpenSWAN server from our California region Windows-based EC2 instance, which currently exists on a public subnet. So we have successfully established the connectivity between two VPCs, or you can say between on-premises and Amazon Cloud. So this is how you can configure VPN connection for the secure connectivity within your on-premises to Amazon network. Okay, so now we have successfully set up our AWS site-to-site VPN, Transit Gateway, and NAT Gateway. So this is end of section 1 of this video. Now let's jump back to the slide where we will solve a few exam questions. Question number 1. A company is building a serverless application that runs on an AWS Lambda function that is attached to a VPC. The company needs to integrate the application with a new service from an external provider. The external provider supports only requests that come from public IPv4 addresses that are in an allow list. The company must provide a single public IP address to the external provider before the application can start using the new service. Which solution will give the application the ability to access the new service? Option A. Deploy a NAT gateway, associate an elastic IP address with the NAT gateway, configure the VPC to use the NAT gateway. Deploying a NAT gateway will allow the Lambda function to access the internet through the NAT gateway and use the elastic IP address as its public IP address. The VPC should be configured to use the NAT gateway as it is default route. This seems to be the correct answer, but let's discuss available options as well. Option B. Deploy an egress-only internet gateway, associate an elastic IP address with the egress-only internet gateway. Configure the elastic network interface on the Lambda function to use the egress-only internet gateway. An egress-only internet gateway is used to provide IPv6-only VPCs with internet access. It does not provide a public IP address for the Lambda function to use, so this is not the correct answer. Option C. Deploy an internet gateway, associate an elastic IP address with the internet gateway, configure the Lambda function to use the internet gateway. An internet gateway is used to provide internet access to resources in a VPC. However, it does not provide a public IP address for the Lambda function to use, so this is also not the correct answer. Option D. Deploy an internet gateway, associate an elastic IP address with the internet gateway. Configure the default route in the public VPC route table to use the internet gateway. Configuring the default route in the public VPC route table to use the internet gateway will not provide a public IP address for the Lambda function to use, so this is also not the correct answer. To enable the serverless application to access the new service, the company needs to provide a public IP address that is in the external provider allow list. Since the application runs on AWS Lambda function that is attached to a VPC, the solution is to deploy a NAT gateway and associate an elastic IP address with it. The VPC should be configured to use the NAT gateway as its default route. This will allow the Lambda function to access the internet through the NAT gateway and use the elastic IP address as its public IP address. Therefore, correct answer is option A. Question number 2. Example Corporation has an on-premises data center and a VPC named VPC-A in the Example Corporation AWS account. The on-premises network connects to VPC-A through an AWS site-to-site VPN. The on-premises servers can properly access VPC-A. Example Corporation just acquired any company which has a VPC named VPC-B. There is no IP address overlap among these networks. Example Corporation has paired VPC-A and VPC-B. Example Corporation wants to connect from its on-premises servers to VPC-B. Example Corporation has properly set up the network ACL and security groups. Which solution will meet this requirement with the least operational effort? Option A. Create a transit gateway, attach the site-to-site VPN, VPC-A and VPC-B to the transit gateway. Update the transit gateway route tables for all networks to add IP range routes for all other networks. Creating a transit gateway and attaching the site-to-site VPN, VPC-A and VPC-B to the transit gateway will allow Example Corporation to connect from its on-premises servers to VPC-B with the least operational effort. The transit gateway route tables should be updated for all networks to add IP range routes for all other networks. Seems to be the correct answer, but let's discuss all available options. Option B. Create a transit gateway. Create a site-to-site VPN connection between the on-premises network and VPC B, and connect the VPN connection to the transit gateway. Add a route to direct traffic to the paired VPCs and add an authorization rule to give clients access to the VPCs A and B. Creating a site-to-site VPN connection between the on-premises network and VPC B and connecting the VPN connection to the transit gateway will not meet the requirement with the least operational effort. So this is not the correct answer. Option C. Update the route table for the site-to-site VPN and both VPCs for all three networks. Configure BGP propagation for all three networks. Wait for up to 5 minutes for BGP propagation to finish. Updating the route table for the site-to-site VPN and both VPCs for all three networks and configuring BGP propagation for all three networks will not meet the requirement with the least operational effort. So this is also not the correct answer. Option D. Modify the site-to-site VPN's virtual private gateway definition to include VPC A and VPC B. Split the two routers of the virtual private gateway between the two VPCs. Modifying the site-to-site VPN's virtual private gateway definition to include VPC A and VPC B and splitting the two routers of the virtual private gateway between the two VPCs will not meet the requirement with the least operational effort. So this is also not correct. To connect from example corporation's on-premises servers to VPC B with the least operational effort, the company should create a transit gateway and attach the site-to-site VPN, VPC A and VPC B to the transit gateway. The transit gateway route tables should be updated for all networks to add the IP range routes for all other networks. Therefore, option A is the correct answer. Question number 3. A company has migrated a legacy application to the AWS cloud. The application runs on 3 Amazon EC2 instances that are spread across 3 availability zones. One EC2 instance is in each availability zone. The EC2 instances are running in 3 private subnets of the VPC and are set up as target for an application load balancer that is associated with 3 public subnets. The application needs to communicate with on-premises systems. Only traffic from IP addresses, company IP addresses range are allowed to access the on-premises systems. The company security team is bringing only one IP address from its internal IP address range to the cloud. The company has added this IP address to the allow list for the company firewall. The company also has created an elastic IP address for this IP address. A solution architect needs to create a solution that gives the application the ability to communicate with the on-premises systems. The solution also must be able to mitigate failures automatically. Which solution will meet this requirement? Option A. Deploy 3 net gateways, one in each public subnet. Assign the elastic IP address to the net gateways. Turn on health checks for the net gateways. If a net gateway fails a health check, recreate the net gateway and assign the elastic IP address to the new net gateway. While using net gateway is a good approach, ALB is primarily used for distributing incoming traffic to multiple targets, not for outbound communication. Also, turning on health checks for the net gateway in this context is not the optimal approach, so this is not the correct answer. Option B. Replace the application load balancer with the network load balancer. Assign the elastic IP address to the network load balancer and turn on health checks for the network load balancer in the case of the failed health check. Redeploy the network load balancer in different subnets. Similar to option A, the NLB is designed for incoming traffic distribution, not outbound communication. It is not the appropriate choice for this scenario. Option C. Deploy a single net gateway in a public subnet. Assign the elastic IP address to the net gateway. Use Amazon CloudWatch with the custom metric to monitor the net gateway. If the net gateway is unhealthy, invoke an AWS Lambda function to create a new net gateway in a different subnet. Assign the elastic IP address to the new net gateway. This solution is designed to provide both reliability and automation. meeting the specified requirements for communication with on-premises systems while mitigating failures in a dynamic and responsive manner. Therefore, this is the correct answer. Option D. Assign the elastic IP address to the ALB, create an Amazon Route 53 simple record with the elastic IP address as the value. Create a Route 53 health check. In the case of a failed health check, recreate the ALB in different subnet. The ALB is used for load balancing incoming traffic and it's not suitable for outbound communication. Additionally, using Route 53 health checks to recreate the ALB may lead to unnecessary disruption for outbound communication. So, option D is also not correct. Question number 4. A company needs to migrate an on-premises SFTP site to AWS. The SFTP site currently runs on a Linux VM. Uploaded files are made available to downstream application through an NFS share. As part of migration to AWS, a solution architect must implement high availability. The solution must provide external vendors with a set of static public IP addresses that the vendor can allow. The company has set up an AWS Direct Connect connection between its on-premises data center and its VPC. Which solution will meet these requirements with the least operational overhead? Option A. Create an AWS Transfer Family server. Configure an internet-facing VPC endpoint for the Transfer Family server. Specify an elastic IP address for each subnet. Configure the Transfer Family server to place files into an Amazon Elastic file system that provide deployed across multiple availability zones. Modify the configuration on the downstream application that access the existing NFS share to mount the EFS endpoint instead. AWS Transfer Family provides fully managed SFTP, and creating an internet-facing VPC endpoint reduces the exposure to the public internet. This enhances security and minimizes operational overhead. Assigning elastic IP address provides a static public IP address that external vendors can allow, ensuring stability. Using EFS for storage allows the solution to be highly available across multiple availability zones, and modifying downstream application to mount the EFS endpoint instead of the existing NFS share is a straightforward adjustment. This seems to be the correct answer, but first, let's evaluate other options as well. Option B. Create an AWS Transfer Family server. Configure a publicly accessible endpoint for the Transfer Family server. Configure the Transfer Family server to place files into Amazon Elastic file system that is deployed across multiple availability zones. Modify the configuration on the downstream application that accesses the existing NFS share to mount the EFS endpoint instead. Having a publicly accessible endpoint might introduce security concerns, and it generally increases operational overhead due to the need for managing public access. So, this is not the correct answer. Option C. Use AWS Application Migration Service to migrate the existing Linux VM to an Amazon EC2 instance. Assign an elastic IP address to the EC2 instance. Mount Amazon Elastic file system to the EC2 instance. Configure the SFTP server to place files in the EFS file system. Modify the configuration on downstream application that access the existing NFS share to mount the NFS endpoint instead. This option involves migrating the existing Linux VM to EC2 instance, introducing additional complexity and operational overhead. It does not leverage fully managed service like AWS Transfer Family and EFS, so this one is also not correct. Option D. Use AWS Application Migration Service to migrate the existing Linux VM to an AWS Transfer Family server. Configure a publicly accessible endpoint for the Transfer Family server. Configure the Transfer Family server to place files into Amazon FSx for Lustre file system that is deployed across multiple availability zones. Modifying the configuration on the downstream application that accesses the existing NFS share to mount the FSx for Lustre endpoint instead. This option involves additional complexities with AWS Transfer Family and FSx for Lustre, making it more operationally intensive than needed. So this one is also not the correct answer. Therefore, option A, the most suitable choice for achieving high availability with the least operational overhead in this scenario. Alright, so this is it for today. I hope you enjoyed this lecture. Thank you all for attending today's class at 591 Lab. We hope you found the material informative and helpful. Remember, practice is critical to mastering any new skill, so review the course content and keep practicing with 591 Lab help and support. If you have any questions or concerns, please don't hesitate to contact us. We appreciate your participation and look forward to seeing you in our future classes. I would like to request you please subscribe to our channel, like the video and hit the bell icon. Your support goes a long way to enabling us to create more valuable content like this. Have a great day.